The anomalous magnetic moment of the electron probably represents the single best test of quantum electrodynamics ever. In fact, the experimental result agrees with the theoretical result to such a ridiculous number of significant figures, it likely represents the best confirmation of any physical theory humans have ever come up with. I think it's been calculated out to 3 loops at this point, and it agrees to something like 8 or 9 significant figures. It's pretty insane. In this video, however, we're not going to take it to quite that many loops. What I am going to show you is how to calculate the one-loop contribution to the anomalous magnetic moment of the electron. This is the calculation that Feynman famously got right, and also I think Julian Schwinger around the same time. Here is the table of contents describing what I'm going to be covering. Let's get started. The first step to perform when studying quantum loop corrections to the anomalous magnetic moment of the electron is to figure out what class of quantum loops actually yields a quantum correction to the electron's magnetic moment. The magnetic moment represents the electron's only capacity to interact with an external magnetic field. So the relevant physical process here is an electron reacting with a virtual photon from an external magnetic field as it scatters off of such a magnetic field. This gives us the following general Feynman diagram, where the nature of the reaction may involve loops. At lowest order, of course, it'll just be a straight loop-free vertex, but this accounts for the fact that there's going to be a ton of loop corrections. It's just generally of this form. Because the magnetic moment of the electron represents the electron's direct coupling to an external magnetic field, quantum loop corrections to the electron lines or photon lines separately from the vertex can't affect the magnetic moment. We therefore see that only quantum corrections to the vertex function itself can contribute to the magnetic moment of the electron. This means that we can ignore quantum fluctuations in the electromagnetic field for this calculation without loss of accuracy. So the Feynman rule for the virtual photon will just be the Fourier transform of the classical 4-vector potential corresponding to a pure static magnetic field. Also, this means that there is no loss of accuracy as a result of taking the electron lines to be on-shell external electron lines, thus ignoring quantum fluctuations in the electron field. If we take the general quantum-corrected vertex function to be represented by gamma mu, so the one including all the vertex functions, then Feynman's rules tell us that the Feynman amplitude associated with the above Feynman diagram is this thing. Our efforts to compute quantum corrections to the magnetic moment of the electron will center around this quantity. From here, the first step in the anomalous magnetic moment calculation is to use general arguments about physical quantities relevant to the problem to narrow down the general form of the quantum-corrected vertex function considerably. Once the basic form has been figured out, in terms of 2 scalar form factors, one can work out how the form factors contribute to the magnetic moment of the electron and ultimately the Landé G factor. I'm not entirely sure how to pronounce this name here, but I'm doing my best. Then a direct computation of the one-loop Feynman diagram contribution to the vertex function can be performed. First, the correction yielded by the one-loop graph, it takes the form of a Feynman integral, must be added onto the 0th order vertex function, which is just the ordinary vertex function. This quantity can then be compared to its expression in terms of the 2 form factors that will have already been derived. From this comparison, one can extract the values of the form factors to the one-loop order. They end up consisting of separate terms from the Feynman integral, and one of them includes the contribution of the classical term, the lowest order term. The integration can then be performed to arrive at the relevant form factor values. These form factor values can then be used to calculate the correction to the anomalous magnetic moment. We can use arguments about behavior under Lorentz group transformations to begin narrowing down the form of the general quantum-corrected vertex function. Let's start with this. We know that the following quantity transforms like a vector under Lorentz transformations, and the Lorentz group generally. We therefore know that the general quantum-corrected version of this quantity must transform identically, because if it doesn't transform like a vector too, then the theory wouldn't be Lorentz invariant. And we also know that the following quantity transforms like a Lorentz scalar, this one. Therefore, given these facts and the limited number of quantities that show up in the theory, the general quantum-corrected vertex function can only depend on these quantities. If one includes any other quantities, then either one is introducing a new random quantity into the theory, or this quantity won't transform like a vector. If we mandate both, then this is the complete set of quantities capital gamma mu could possibly depend on. It turns out that we can reduce this set further by using the Dirac equation satisfied by the on-shell spinors, which are on either side here. These are the equations those spinors satisfy, and then these are those same equations rearranged in a way that makes it absolutely clear how they reduce this set. They convert these slash momentum vectors into mass factors. So that previous set is now reduced down to this. Given this, the most general possible form for the quantum-corrected vertex function is this quantity here, where these functions could possibly have dependence on E and M, so that's how they come into this if it wasn't clear. The first step in narrowing down what the unknown scalar functions are is to use the Ward identity, which must be satisfied by the vertex function. If you don't remember, this is a consequence of gauge invariance. Anyway, writing this out gives us the following, this here. So this is the Ward identity right there, and I have simply plugged in the value of capital gamma mu so that we can start working with this. The way in which the Ward identity helps us simplify this quantity is by allowing us to ignore this last term. We can prove that the coefficients on the other terms vanish for the general case, ultimately leaving us with an equation setting this quantity here equal to 0 generally. We can first prove that the coefficient of this B scalar quantity vanishes identically using momentum conservation. Momentum conservation at the vertex gives us this relation. Applying this to that coefficient gives us this result, which of course zeros. If you don't see how that happens, we end up with a difference of two squares, which both equal the mass squared and cancel each other, therefore giving 0. Therefore, the Ward identity for the general quantum-corrected vertex function reduces to this, so we're one step closer to proving that C has to be 0. We can then use the same momentum conservation relation together with the Dirac equation to show that the coefficient of this A scalar vanishes again when sandwiched between the spinors that this quantity, gamma mu, is sandwiched between. We can see by plugging that in, we arrive here, and then we can apply the Dirac equation to get us here, and then these masses cancel. Inserting this into the Ward identity reduces it to this. Now we can prove that this coefficient isn't 0. Specifically, we'll do this using momentum conservation again. So if we plug this value of Q in, mandated by momentum conservation, we see that it's necessarily not equal to 0. This ultimately reveals that C has to be equal to 0. So there's our result that simplifies gamma mu down. That's the value of the Ward identity in this particular problem. With this done, to get it into standard form, we must apply the Gordon identity, which is this. Now I have proven the Gordon identity on the side here in this box, but I'm not going to bother going through that. You can pause it and look at it. It's pretty straightforward. I'm going to move on with the main text. The Gordon identity can be rearranged for application to the corrected vertex function. Specifically, if we're looking to get the general vertex function into standard form by using the Gordon identity, we want it rearranged like this. And the reason why this is valuable is then we can make a nifty substitution. We can substitute this quantity in for this sum of momentum vectors divided by 2m, which almost shows up here. So we're going to have to mess with some factors of 2m in the numerator and denominator to get it to match up exactly, but we can easily do that. Doing that gives us this, and then we can see that there's two different scalar factors that we're dealing with, one that's the sum of a and b, and one that's just b. The standard name for those two independent scalar functions are f1 and f2. So we're almost done getting this into standard form. There's one more thing we need to do. We need to replace this argument with q squared. And that just reflects the fact that dependence on p and p prime can actually only come into these factors via q squared. Now the reason is the following. f1 and f2 are scalar functions, and they are sandwiched between on-shell spinors. Therefore, any other dependence on p and p prime beyond q squared can be eliminated via the Dirac equation or the Gordon identity. So we're free to actually write it like this. The f functions, as I think I've already said, are called form factors, and the next step is to see how the magnetic moment of the electron is affected by these form factors, which is the subject of the next section. We will work out the form of the quantum-corrected magnetic moment by comparing the Feynman amplitude from the introduction to a very recognizable Hamiltonian from classical physics. This comparison can, of course, only be done after extensive manipulation of the Feynman amplitude, including taking the non-relativistic limit. So let's get started. In the introduction, we arrived at the Feynman amplitude for an electron scattering off of a magnetic field, including vertex corrections. The Feynman amplitude is this. Now, considering that the 4-vector potential is supposed to be for a static magnetic field in this problem, we have this. We can plug that into the Feynman amplitude, which gets us here. We can then write this like this by substituting the expression for this in terms of the form factors that we found in. Then, to see how the form factors correct the anomalous magnetic moment of the electron, the first step is to consider the explicit form of the spinors. Specifically, we must evaluate the above amplitude, this thing, using the explicit formulas just written out, these, and then finagle it into a form where we can recognize the magnetic moment by comparison to the aforementioned familiar Hamiltonian. Evaluating with the explicit spinors makes the latter step possible. Beginning with the first term in the amplitude, this one, we see that this is just a scalar and it's just going to multiply whatever we ultimately manipulate this into, so it's not really of interest. The rest of the first term is something we expect to be interesting when we stick the spinors in. So if we start with this quantity here, remember the form of U bar, and then insert all of the gamma matrices, we get to here. Then we can insert the form of the spinors and multiply it all out, which gets us here. We are considering the magnetic moment of the electron, which is a scalar property of the electron that therefore can't be affected by relativistic corrections. So we can safely simplify the math by taking the non-relativistic limit. In the non-relativistic limit, meaning low kinetic energy, where these rough equalities are true, this thing simplifies down to that, and we can do some factoring to get this. Then we can employ this identity for the sigma matrices. Plugging those in gets us to here. Including only terms linear in Q, the non-relativistic limit, we arrive at this. This is the non-relativistic limit of the first term of the amplitude under consideration. The next step is to take the non-relativistic limit of the second term in the amplitude. Like when we were taking the non-relativistic limit on the first term, here in the second term when we take the non-relativistic limit and manipulate it into a more useful form, we're going to ignore the form factor because it's just a scalar multiple. In this low energy limit, the photon energy is negligible, so we find that this rough equality is true. Then we can remember this is the form of the sigma matrices and insert that in, as well as breaking up this U bar quantity into U dagger and this gamma zero factor. Inserting the definition of the spinors and ignoring terms nonlinear in Q brings this down to that. Then after taking the non-relativistic limit on all other parts of the expression, namely this part here, we arrive at this final result. Now one can insert the non-relativistic limit of both terms into the amplitude. In this limit, the amplitude ultimately works out to be this. Now you may notice that when we plug in the non-relativistic limit of the multiples of the form factors in the first and second terms, we're also inserting the form factors evaluated at Q squared equals 0. This is part of the non-relativistic limit. Remember, we're ignoring anything of order Q squared and higher as a part of that limit. So because they're purely a function of Q squared as far as momentum variables go, we must evaluate them at 0 as a part of this limit. Now one can plug in the definition of the momentum space magnetic field, which comes from Fourier transforming the usual position space quantity. If we Fourier transform this to momentum space to get the momentum space version we were talking about, and then write it in index notation, we find this quantity here, and we can plug that in, or rather notice that it shows up here, and then just substitute the magnetic field for that quantity in parentheses, we get to this. In this quantity, we can identify the spin vector expectation value here. So then we just have a dot product between the spin, or the average spin, and the magnetic field, which brings us to here. Now, to extract the electron's magnetic moment from this non-relativistic limit of the quantum correction inclusive Feynman amplitude, we need to compare it to the classical limit, not to be confused with the non-relativistic limit, which we took on this one, but still included the quantum corrections. The reason why this will work is the following. We know how to write the classical and non-relativistic interacting Hamiltonian density for such a system. It's just this Hamiltonian there. And through the S operator and its associated S matrix, we can see that the first order classical contribution to the Feynman amplitude for a particle with spin scattering off of a magnetic field is the following, given the classical Hamiltonian just written, this quantity here. We can then compare this to the above established form for the quantum corrected version in the non-relativistic limit, this quantity here, and extract the quantum-corrected magnetic moment by inspection, this quantity here, ultimately. From this, we can identify the quantum-corrected Landé G factor, this here, and that is how quantum corrections affect the magnetic moment. We can now go on to actually computing the first-order contributions to F1 of 0 and F2 of 0. The goal now is to compute F1 of 0 and F2 of 0 to one loop by first writing down the one-loop vertex correction using Feynman's rules, and then manipulating the sum of it with the gamma matrices into a form where the one-loop contributions to F1 of q squared and F2 of q squared can be read off. They can then be evaluated at q squared equals 0. To make this process easier, I will introduce some new notation. I have so far already introduced the quantity capital gamma mu as the complete quantum corrected vertex function. Now, strictly speaking, as you've noticed from the formulas, it's not quite the vertex function. If you multiply it by negative IE, it becomes the vertex function, so it's sort of the quantum corrected gamma matrices-ish. It's just a constant factor away from the vertex function, so it's a proxy for that, so you'll usually hear people talking about it like that. Because in this calculation we are only considering quantum corrections to one loop, I introduce the quantity gamma 1 mu, which is the vertex function corrected to one loop. Also, I will use delta gamma mu to denote the quantum correction part of gamma mu, and delta gamma 1 mu will be used to denote the one-loop quantum correction, aka the one-loop part of delta gamma mu. So we have these two relations based on those definitions. From here, I will also label the one-loop contributions to F1 of q squared and F2 of q squared with the symbols F11 of q squared and F12 of q squared. We therefore have these two analogous relations based on these last two definitions. With the notation sorted out, we can move on to the actual computation of the one-loop contribution. The one-loop contribution to the vertex function is described by the following Feynman diagram, unsurprisingly. Using the Feynman rules for quantum electrodynamics, this diagram translates to this term, and since it's the one-loop quantum correction to the vertex, we get delta gamma 1 mu as per the notation that I explained above, and because this, like the whole gamma mu in our calculation, is being sandwiched between spinors, I've sandwiched them between spinors here also, which is just treating these electrons as on-shell external ones, and they'll be useful in future manipulations extensively. Now we can start manipulating this. First, neatening up some of the notation gets us to here. Then we can multiply the numerator out. There are a number of factors there, and we can multiply those out. That gets us this. I still leave the spinors undistributed because they don't really help us simplify things, at least yet. Next, we can rewrite the Feynman slash notation in index notation, which gives us this. And this makes it especially obvious to see how to use identities for the gamma matrices like this to simplify it quite a lot. Specifically, applying them gets us directly to this. We can neaten this up some more to get to here. Now, even neatened up, this is still a rather nasty integral, and it is also completely unclear how to break it apart into f11 of q squared and f12 of q squared. Of course, we'd need to add on the gamma mu, which is the zeroth order part, before we could do that anyway. But still, even then, it's totally unclear how to do that. So clearly, we are going to have to manipulate this significantly in order to be able to handle it. The first of these manipulations is called the Feynman parameter trick. It consists of rewriting this in terms of an additional integration. It ends up being the case that in this new form, the momentum integration is computable. One can then do the parameter integral that was just mentioned afterwards. The particular integral identity that the Feynman parameter trick uses is this one here, which allows us to rewrite the denominator of this integral in this nice useful form here, where d in the denominator there is equal to this. With this fact, we can rewrite the entire Feynman loop integral in this nice form here, where I've defined this quantity n mu to equal that. It may not seem like the situation has been improved much. The integral we must compute still looks kind of insane, but this does actually leave us in a better position. Unlike without the Feynman parameter trick, this integral can be worked into a computable form with some further simplification and a change of integration variables. The change of integration variables will be from k to L, where L is defined this way, and I mean this vector-wise. I'm dropping the index notation there just to simplify things, but this is true component-wise for the L vector, K vector, Q vector, and P vector. Let's start this process of simplification and variable changing by working with D, which is the factor that shows up 3 times in the denominator. As given above, d takes on this form. The delta function in the Feynman parameter trick integral identity forces this constraint, which simplifies this term to that. We can then eliminate k prime by inserting its value in terms of the other momentum variables. We see that k prime squared shows up, so we can compute k prime squared. Then we can do this square here, that's the x3 coefficient, which equals that. Inserting both of those things into d gives us this. We can simplify further, mostly by factoring, and we notice another one of these sums here, which via that same identity imposed by the delta function just equals 1, so it simplifies down to here. It is now time to change variables from k to L. The easiest way to do this is to evaluate L squared minus d, and then solve for d. Recall that L equals k plus x2q minus x3p, therefore L squared is this quantity, which means that L squared minus d is this. We can simplify this considerably, again making use of this in that process, down to here. We can simplify this further using this identity, because we see that when we actually square p prime squared, which must equal n squared, we also have a p squared in the expanded out version of that square through momentum conservation. So we get another m squared here. We can subtract m squared from both sides, and we realize that this quantity here is actually equal to 0, which via simplification I've revealed as the coefficient of this x2, x3 term, so that just zeroes out, and we get that L squared minus d just equals this. We have that this is entirely L independent, and the convention is to hide most of this L independent part in this delta quantity there, except for the I epsilon, and so we end up with this equation. But then we can solve for d, as I said above, and we arrive at this convenient form. Now, the reason why this is a convenient form is because we're really mostly focused on L dependence here, at least for this first integration. So it reveals that there's this L squared in there, and then just hides all the other L constant stuff in this delta. So it really highlights what we need to know and hides all the other junk. Now, with d sorted out, we can focus on n mu. With n mu, it is easiest to change variables first and then simplify. The change of variables will require these two identities, which can be manipulated into a form that's directly substitutable into n mu, which is these two equations. Substituting that in gets us here, and I've also written some of the Feynman slash notation in index notation. We can multiply this out and rearrange it further to get to this. This is now written as a function of L mu instead of K mu. The next job is to simplify it and integrate. This simplification and eventual integration begins with the following. Because n mu is the numerator of an integrand that is being completely integrated over all space, we can simplify it using identities that are only true under such a complete integration. I will call these things integrand identities, and they will be derived from the following two integral identities. The first of the two integral identities is this one. We can see that this integral must be 0 because d is an even function of all components of L mu, so the integrand is odd given the factor of L mu in the numerator. The second and final integral identity that we need is an alternative expression for this integral here. Well, specifically the integral identity is this set equal to the alternative expression, but you get what I mean. All L mu vector components are integrated over all possible values, therefore the integral cannot depend on the direction of L mu in 4 space. This means that it must be uniquely specified by its scalar contraction. The same is true for this integral right here. In this integral, the integrand doesn't even depend on the direction of L mu in 4 space. In that regard, the integral is redundant. In any case, this means that these two integrals are equal because their scalar contractions are equal. So this is the integral identity that I was talking about. This is the second one we need. Because of these integral relations and the fact that the Feynman integral is such an integral, we can freely manipulate the integrand with the following integrand identities without loss of accuracy. We can take terms like this to 0 and terms like this to g mu nu holding the indices times L squared over 4 times the same denominator. Because the Feynman integral contains a factor of 1 over d cubed as its denominator, this implies the following relations for directly manipulating n mu without loss of accuracy. These two, where we just forget the d cubed. Now we can return to manipulating n mu. The last expression for n mu that we had was this. We will begin simplification by ignoring terms linear in L mu justified by the L mu goes to 0 identity for n mu given right there. Doing that simplifies it down to this. Next, we can analyze the first term. We can see that within the integral it equals the following because of the second n mu identity, this one. We just get to here. Of course, I have employed the gamma matrix identity given there in the last step to get from here to here. Inserting this gets us to this, which is already looking quite a bit better than that nasty thing we started with for n mu. Now working on the second term, this one, well, with the spinors in the factor of 2, which I'll call h mu, we can manipulate that and simplify it quite a lot. And when we do that, we'll use these identities extensively. We can use relation number 1 to manipulate the second two factors, and we can then use relation number 4 and number 2 in sequence to manipulate the first two factors, yielding this. So these are the second two factors, and these are the first two factors. I'm ignoring 2 when I say the first two factors. We can now do some factoring in the first set of parentheses and get to here. In the newly factored part, we can apply relation number 3, which allows us to exchange dependence on x2 and x3 for just dependence on x1 in these parentheses here. We can now expand this out by distribution, which gives us this. Now we can work on the yellow highlighted factor. There's some simplification we can do with that, using the following gamma matrix identity specifically. Now this is a bizarre gamma matrix identity. It's perfectly valid, but it's kind of an exotic one. I don't think I've ever used it for any other calculation than this. With some index juggling, we can easily substitute that in, which gets us here. Now, we know that this is a symmetric matrix here, this product of q's, and we know this Levi-Civita symbol is an antisymmetric matrix, and they're contracted, which will just give 0, so that term vanishes, and then we can simplify it the rest of the way down here just by doing some index juggling and combining like terms. We can prove that the first term in this rewritten factor gives 0 when sandwiched between spinors. This is done with relations number 4, number 1, and number 2 in that order. Relation number 4 is momentum conservation and gets us from here to here, and then relations number 1 and 2 get us from here to there, and then we see the masses cancel. So therefore, we have that when sandwiched between spinors, the yellow highlighted factor can be rewritten in this way. Inserting that back in gives us this here, where we see that factor. Now we can consider the factor that is highlighted in green. This factor can be rewritten using the Dirac-Clifford algebra written here in this manner. We can consider this product of gamma matrices to be the first term in an anti-commutator, and then we can subtract the second term to the other side with the metric tensor on it, the other side of this Clifford algebra, and that'll give us an equality for this product of gamma matrices that we can substitute in for it. If we insert this in and then refactor, we ultimately get to here. Then we can simplify this with relation number 3. This is relation number 3, it implies this, and that allows us to exchange pure x3 dependence for x1 and x2 dependence right there. We can now rewrite the blue highlighted product. In the expression that we care about, this factor is sandwiched between spinors. So in addition to relation number 4, we can also use relation number 2. Relation number 4 gets us from here to here, it's just momentum conservation, then number 2 gets us from here to here. And then in the same way that we just did, we can use the Dirac-Clifford algebra to rewrite a product of gamma matrices, specifically the product in this second term right there. We can rewrite it like this. Substituting that in gives us this. Then we can use relation number 1 to exchange this p slash for an m, and then that makes this term the same as that one, so we can combine them and we get to this. Then we can insert this and do a bunch of refactoring and ultimately get down to here. I wrote out all the steps to keep you from being able to get lost. We can now insert the second term back into n mu. The last expression we had for n mu is this one. Inserting a new expression for the second term and refactoring more gives you this. Then we can manipulate this a little bit further using the delta function imposed identity, the x1 plus x2 plus x3 equals 1 identity, to get this. The last term is an odd function of x1 and x2, and the denominator of the integral is an even function of x1 and x2. So overall, the last term of the integrand is an odd function of x1 and x2. Therefore, this term vanishes in the integral. It can thus be ignored, which allows us to shorten it down to this. The next step is to rewrite this in a way that makes apparent how this Feynman integral contributes to the two form factors, at least once it's inserted back into the integral and added to the gamma matrices. The first step in this process is to use the Gordon identity again. Remember, we proved it above in that box. This identity implies this rearranged version of it, and then we can insert it, basically replacing this p prime plus p part there with the gamma matrices and this sigma matrix there. That allows us to write n mu as this. If we insert this back into the main integral, we have this expression, where we've established that d in the denominator is just equal to that. Now that we have simplified this quantity down and changed variables to a set that is more ideal for integration, we can consider this quantity with the gamma matrix back in, the zeroth order part back in full, in order to extract f11 of q squared and f12 of q squared. This whole gamma 1 mu in full is this quantity right here, where I've pulled out the spinors now just to get a straight up expression for gamma 1 mu. We can break this quantity into two different terms that are written here, in order to pull out the coefficients of gamma mu and then this factor here. And the reason why that's useful is because those coefficients are f11 of q squared and f12 of q squared, which are just these. So we finally identified those. Now that we've identified these two quantities, we can start working out the L integration. By looking at them, we notice two kinds of L integrations. Taking the limit as epsilon goes to 0, so d equals L squared minus delta, instead of also having that I epsilon term there, the two integrations that we notice are these two. This is the most common one, it shows up in both, and then this one shows up in the f11 of q squared in addition to this one, whereas f12 of q squared just contains this one. In this section, we're going to compute these integrations. Because of the minus signs in the Minkowski metric, it is useful to perform a Wick rotation before integration, which is just a complex coordinate transformation of a special type. We're just taking L naught to minus I L naught, so the components of the L vector overall are just these. The integrals in this situation become this through simple direct substitution. Now, because the integrand depends only on the magnitude of LE, i.e. the radial coordinate, where E stands for Euclidean because we're Wick rotating to a four-dimensional Euclidean space, it is advantageous to switch to spherical coordinates, seeing as the angular integral will just decouple from the radial part. Doing that gives us these two results, and then the angular integrals are really easy to do because there's no angular dependence anywhere in this, so we just get that the angular part is equal to the surface area of a unit 3 sphere, which is just 2 pi squared. So we have these two results. Now we can simplify these a little and write them out so that we can do a third coordinate transformation. The first coordinate transformation, of course, was from K to L. The second one was to these hyperspherical coordinates for four-dimensional space, and now this third one will be this A change of variables. Now the main change I'm making here to make it super double extra easy to make this change of variables to A is I'm bothering to bring a factor of LE right next to the differential, because dA equals 2 LE dLE. So let's take this first integral here. I'm going to do these separately now because I have to write out a bit more math to really show you what I'm doing. If we substitute this in, we get to here. Then we can multiply this out and set it up for easy doing with the power rule. Applying the power rule gets us to this, and then we can plug in the integration limits, which gets us here. And then we can manipulate this algebraically in order to get it into the final form. So then we have this value for the first of the two integrals we care about. Then we can use the same change of variables, the same final third one on that second integral to do it. The only difference between this integral and the first one is the factor of LE squared in the numerator. So performing basically the same process actually gives us three terms this time, which we integrate just like before, and we can manipulate into a similar form, and we get this result. So this is the other integral that we needed. Now that we've done the key integrations we need, we can use them to actually calculate out these form factors. I'll start with f11 of 0. So f11 of q squared was identified to be this quantity. If we evaluate that at q squared equals 0, we arrive at this. We can then isolate the L integrals, which gets us here, and then we can insert the value of d to get it ready for substituting the values of those L integrations in. And then in this table, I've shown how to figure out what those specific L integrals are. Really, we're just picking n equals 3, that's really all we have to do. The actual integration we already did for general n. That gives us these two results. We can then insert them and simplify. So we see that we have a divergence. If we had cut off the momentum integration at some finite value instead of taking it to infinity, of course the result would not have been divergent. However, we must naturally take the integration limit to infinity, which yields an infinite result, because of the extra L squared in the numerator of the second integral compared to the first integral, which is convergent. Divergences in loop integrals that arise when one takes the integration limits to infinity as a result of too many momentum factors in the numerator are called UV divergences. In the case of this particular calculation, it turns out to be a log divergence. This fact can be worked out by using a suitable regularization scheme. However, the particular strength of the divergence isn't relevant for this calculation, so I will not waste time showing this. The usual thing to do to handle this is to subtract off the divergence at zero momentum and then absorb it into an infinite renormalization constant. Renormalizing in a mathematically rigorous manner would require us to first regularize the divergent integral, for example with dimensional regularization, and then renormalize, and then eliminate the regularization scheme. For dimensional regularization, this would mean returning to 4 dimensions. Thankfully, we don't have to worry about the complete renormalization process. All we need to do is do the subtraction and then evaluate f11 of q squared at q squared equals 0. f11 of q squared with the divergence subtracted out at zero momentum is this, where to make this written clearly, I define this omega of q squared quantity. So then if we evaluate f11 of q squared at q squared equals 0, we of course just get 1. And that is our final result for f11 of 0. With f11 of 0 taken care of, we can move on to computing f12 of 0. This quantity contains no divergent integrals and is therefore much easier to handle, seeing as it requires no discussion of renormalization theory. This is f12 of q squared, simply equals that. We can then rearrange this to isolate the L integration and insert the value of d, which tells us that we need to find the value of this integral, but that's of exactly the form we already calculated, just with n equal to 3, so plugging that in, we get this result. We can then insert that and simplify it, ultimately down to this, and then we can insert delta, which gets us here, and then we can evaluate it at q squared equals 0, which gets us here. Then we can do some cancellation between the numerator and denominator because we've got some like factors there. Of course, I flipped this under the square, but that's just at a cost of a sign, and the square eliminates the sign. Then I brought this factor of 2 out here and canceled it against the 4, which got to here. Now we can use the delta function to do the x1 integration, which gets us here. Then we can do the x2 integration, which just cancels this denominator, and leaves us with a very simple integration for x3, which just yields that f12 of 0 is alpha over 2 pi. Now we can go on to use these one-loop form factor contributions that we've painstakingly calculated to actually evaluate the anomalous magnetic moment and the Landé G factor. In section 3, we figured out that the magnetic moment of the electron is this, and in the preceding parts of section 4, we found that f11 of 0 and f12 of 0 are these quantities. So, to one-loop order, the anomalous magnetic moment of the electron and the associated Landé G factor are these. We get this famous result that G equals 2 plus alpha over pi to one-loop order. So now you have seen how to calculate the one-loop correction to the anomalous magnetic moment of the electron. You've seen the full process of isolating how quantum corrections to the vertex function will contribute to the magnetic moment and the Landé G factor, and you've seen how to do the one-loop Feynman integral to calculate out those form factors to the one-loop order. Then you've seen finally exactly what contribution to the anomalous magnetic moment that actually gives. If you like this video, please give it a thumbs up. And don't forget to subscribe. D-Trick out.